velocity and other rates of change.
Dude, that worked so well. Oh my gosh.
Okay, so our problem that we just modeled is an explosion happening underneath a rock, flying up in the air and coming back down. So the first part is, how high does the rock go? We start off by having velocity equals derivative of speed with respect to time. That equals displacement with respect to time multiplied by 160t minus 16t squared, which comes out to be 160 minus 32t feet per second. Velocity is 0 when 160 minus 32t equals 0, or at 5 seconds. So the max height is s of 5 equals 160 times 5 minus 16 times 5 squared, which all adds up to be... So find velocity when height equals 256. S of t equals 160t minus 16t squared equals 256. So we make that equal to 0, and it comes out to be 16t squared minus 160t plus 256 equals 0. You take the 16 out, and that gives you 16 times t squared minus 10t plus 16 equals 0. So you FOIL it, and you get t minus 2 and t minus 8. So t equals 2 seconds, or t equals 8 seconds. So then you do velocity of 2, or v with respect to 2, equals 160 minus 32 multiplied by 2, and that comes out to be 96 feet per second. And you do it of 8 equals 160 minus 32 multiplied by 8, and that also comes out to be negative 96 feet per second. Alright, so now we find the rock acceleration. A equals derivative of velocity with respect to time equals displacement with respect to time multiplied by 160 minus 32t. All of that comes out to be negative 32 feet per second squared. This is acceleration, because it's on its deceleration. So when does the rock hit the ground? Well, it's when s equals 0, because it's on the ground. So 160t, that's a minus sign, 16t squared equals 0, and then you get t equals 0 and t equals 10. So at 10 seconds later, the rock goes thud after our rigged up explosion. So that's it.
I don't think you're getting that ball back.
I'm Travis Furtkamp, and I hate calculus. And rockets.
Okay, what we have here is a graph of a rocket in flight and taking off, and this is a velocity. Velocity of the rocket is on the y-axis, time after launch on the x-axis. The velocity is going to be in feet per second, and then the time is going to be in seconds on the x-axis. So, one might ask, how fast was the rock climbing when the engine stopped? Well, we decided the engine stopped at this point, at point A, because it stopped accelerating. It lost all of its acceleration. So at this point the engine would have cut out, and it would continue at a constant acceleration, but it would no longer be positive acceleration. So how fast was it going at this point? It'd be about 180 or 190 feet per second. Then one might ask, for how many seconds did the engine burn? And so it would be from here to here, because we decided that this whole part of the graph right there was when the engine was burning. So between there, so for about 2 seconds. And then when did the rocket reach its highest point? We determined that it's basically at the end of where the graph is positive. So it has a positive velocity, so it's going up, going up, going up, going up, going up, going up. And then right here, it's no longer going up. So it'd be at its highest point right here. It'd be at the peak of its flight, kind of in this little part of the picture. And that would be after 8 seconds. And then how fast was it falling? In the Y direction, it would be 0. So at that point, it would just kind of be suspended in air. When did the parachute pop out, and how fast was the rocket falling then? Well, the parachute would have popped out right here. At this point, it would start falling. So it's falling, and then the parachute pops out, which is causing it to fall at a lesser rate. So point D is where we decided the parachute would have popped out. And then how fast was the rocket falling then? It was going about negative 100 feet per second, so that just basically means 100 feet per second down. Then how long did the rocket fall before the parachute opened? Well, it began falling at this point right here, and then between here and here, which is where the parachute opened, so at this point, just on your x-axis, it would be about 3 seconds. So between 8 and 11, 3 seconds after 8 seconds after launch. When was the rocket acceleration the greatest? It would be just before point A, just before the engine cut out, would obviously be the point where acceleration would be the greatest. When was the acceleration constant? We'd have a constant acceleration over this. Acceleration is the derivative of velocity. So if you were to take the derivative of this line right here, because the slope is constant, the derivative would be a straight line. So that would signify a constant acceleration. And that is all you need to know.
Minus 10t plus 16t, or plus 16 equals 0.
Dang it.
I'm Travis Furtkamp. I hate calculus. And Matt hate rockets.
Candle, Roman candle, turn around.
Whoa, 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 hey, you're turning it the wrong way, Graham. Come down.